All right, what we're going to talk about now is we're going to talk about activity 323. And 323 is the medium scale integration counters for asynchronous counters. Activity 322, the PowerPoint in there is the same PowerPoint as 321. It's the small scale integration flip where you make it out of the individual flip-flops. Now we're actually going to use a full IC chip with a counter inside of it. Go through that. So let's take a look at this. See if I can get my pen up here. Oops. All right, so medium scale integrated counters. And the one we're going to look at, it's a 74LS93. It's a 4-bit ripple counter. And we're going to take a look at its layout, how to use it. It has some special things that you have to do with these externally that you could do easily if you had the individual flip-flops set up. So, but this is what it looks like. It's a 4-bit ripple counter, and actually, if you take a look at it, we have. Let me get my pen back here. That's not my pen. There's my pen. If you take a look at it, it's got 4 JK flip-flops inside of it, and 2 of them have the Q tied to the clock forward. All right, so really it's kind of a combo. You could make a 3-bit counter out of this. You could tie in the 4th one, make a 4-bit counter. You can use it as a divide by 2. So it's kind of a flexible type IC chip. It's got 2 inputs here, so you can bring a clock in here. You can also bring a clock in down here. It's got 2 controls for resetting. And if you notice, the only outputs, they have the pin numbers on here if you have an IC chip. The only outputs are the Qs. We don't have access to the Q knots. We don't have access to the presets, only the clears, and it's all the clears. They're all tied to this 2-input NAND gate down here. So let's take a look at this. Now, to make a 4-bit counter out of these, this is where you got to tie externally a wire from QA back around to the input on B. And now this is a 4-bit counter, can count 0 through 15 for you or some other count. Once again, since you can't get to the presets here, the only type of modulars counter you can build is one that starts at 0 and goes up to some number, and then you reset it back to 0 again. So that's what this guy's about. So let's take a look here. Here's the actual IC. If you ever use one of these ICs, you probably have to be a little bit careful. If you notice, we're used to pin 14 with 5 volts on it. We're used to pin 7 with ground, and you notice that that's not the case. But we're going to use these in PLD mode. And so this is actually an IC chip. If you buy one of the Project Lead the Way IC kits, these do come in that. Here's the truth tables. Where do you find these truth tables? These are actually out of the data sheets. So here it shows the count going from 0 through 15. Now, here's some important notice to point out to your students. When we used to label a truth table, we'd go A, B, C, D across here with them. And now, if you notice, this is D, C, B, A. So this is just reverse. So D here is our most significant bit of our count. And so this is going to be critical here because we're going to tie some chips together. And we got to remember D is the most significant bit. And A now becomes our least significant bit. So just a good thing to point out to the students here at this point in time. Now, 2 of the things that we're interested in is these 2 resets. And if you notice, if either reset is a low, either one of them is a low, doesn't matter what the other one is, either one is low, then this IC chip, when it has a clock coming in, it will count. If you take the two resets and tie them high, that then clears the 4 flip-flops to all zeros or lows. That basically is your reset back to 0 count. Here we show a connection here, and right away they got this circled right here, this inverter externally. Well, once again, if we want to count up to some count, here they want to count to 12 and they want to reset when they hit 13. We do not have access like we did in the small scale integration. We didn't have access to the Q not pin. So what we have to do is externally put an inverter on here. So let's take a look at this. So we have a 1 here, a 1 here. This is a 0, and this is a 1 here. So that's our number 13 in binary. So that's what we're looking for. What they do is they then, this one's inverted to a 1. So down here we have our NAND gate with 1, 1, 1. And then you go, well, why do they have another inverter right here? Why don't I just have a 4-input AND gate right here? Well, I think what they want to do is they want the students to notice the use of the NAND gate, to use the NAND gate for this feedback circuit for the counter. So I think that's why it's been left in here, other than just, yeah, you could get rid of this inverter and make this a 4-input AND gate in your PLD. Now, if you notice, this comes around. And remember, this, when we match our count, gives us this. The inverter gives us this. So when this goes high right here, the other one, the other reset is high already. You know, it's just sitting up high. So that's when this will reset back to 0. Here's our external QA wired back into the input of B. So this is a 4-bit counter. And they got our clock coming in here. And whoops, sorry about that. If we take a look here, it's falling edge, so when the clock goes on the falling edge, it increments. So this is a MSI, example of MSI, and a modulus counter in MSI. Here they show you the count. Remember, we counted up to 13. So right here, D would have been right here. There's the 1, 1, 0, 1, so that's the D. There's the 1 on the D, very short period of time, then boom, it resets back to 0. So this counts 0 through 12, and you actually see that on your display, and then resets back to 0. Let's see, what are some limitations? Well, we went over some of the limitations. You can't preset it to some count, so you couldn't use this in the random number generator because you had to reset it to a count of 1. You can't do that with this one. It does have all the features in it, though. It's all wired up. That's what makes it nice. And we can only start at 0. And it's only an up counter. We can't make it a down counter. So, and that's pretty much that aspect of that PowerPoint.